All right, here's question 15 on the math subject GRE practice test. Haven't been able to make any of these for the last couple days, but I know there's some people with the test coming up that are pretty eager to see these, so I'll try to get them posted as quickly as I can. The idea with this problem is we have these two different equations, and we're asked for a necessary and sufficient condition for there to be at least one solution. So you might not need it, but I think it really helps to have a graph of what's going on here. So it'd be awesome if you could just recognize that this first equation is the equation of a circle that's centered at the origin with a radius equal to the square root of a. Maybe more generally, the circle centered at x1, y1 with a radius equal to r is given by this equation. Or maybe even more generally, the standard form of the equation of an ellipse that's centered at x1, y1 with what I kind of call the x radius and the y radius. I'm fairly certain those aren't the right terms, but sort of half of how wide it is in the x direction and half of how wide it is in the y direction are given by r sub x and r sub y respectively. So maybe you can just kind of think, if the x radius and the y radius are the exact same, maybe call them r. These would both be r squared, and if I multiply both sides of the equation by r squared, they go away down here and they show up over here. But in that instance, my ellipse would really be a circle, so I'd come up with this equation here. And maybe the most basic circle is the one that's centered at 0, 0. So I got x minus 0 squared and y minus 0 squared as the two terms on the left side of the equation, which is exactly what I have up here. Common mistake to think that the radius of this circle is a. It's not. It's the square root of a, because the number over on the right side of the equation is not the radius. It's the square of the radius. So look at this and think r squared equals a, therefore r equals the square root of a. For this second equation, you might be able to just look at it and know what it looks like. But for me, what I had to do was solve it for y. So I got y equals, I don't know, maybe b times 1 over x. And then I can just look at this and think about it as a transformation of y equals 1 over x. So I know y equals 1 over x is this inverse graph, what rectangular hyperbola maybe. So what I'm doing is I'm taking this graph and multiplying it by b. When it's written in this notation, it kind of looks like a vertical transformation. I'm stretching it vertically. I'm multiplying all the old y coordinates by b. So this point that's on the graph of y equals 1 over x has an x coordinate of 1 and a y coordinate of 1. Under this transformation, the y coordinate would change into b. But instead of thinking about it as y equals b times 1 over x, I could think about it as 1 divided by 1 over b times x. Right, the b is up on the top, loosely speaking. If I want to put it down on the bottom, I got to consider its reciprocal, 1 over b. But the reason I wrote it this way is now it looks like I'm messing with the x, the input to the function, as opposed to the 1 over x, the output of the function. So this is a horizontal transformation, not a vertical transformation. You might think that I'd be multiplying all the x values by 1 over b, but I'm not, because horizontal transformations are always kind of the opposite of what you'd think. So I'm not multiplying the x values by 1 over b. I'm actually dividing them by 1 over b. In other words, multiplying them by b. What I'm saying is this point that had an x coordinate of 1 and a y coordinate of 1, if I think about the transformation this way, would have an x coordinate of b and a y coordinate of 1. Really, all I'm saying is this graph over here kind of sort of looks like this. Sure, good enough. Importantly, it retains the symmetry that the 1 over x graph had. And because I know this other graph, this circle has some really nice symmetries. Maybe I can draw a circle with a radius of the square root of a. It's a pretty bad circle, but you get the point. The two graphs I'm considering in this problem is the red one and the purple one. And if I choose A and B carefully, I can make this red circle big enough to intersect this purple graph, which would mean it would have a solution. The picture that I've drawn has 4 solutions, right? One up here, one over here, one down here, and one over here. And I guess anytime I have solutions in the first quadrant, I'm going to have a corresponding solution in the third quadrant due to all this symmetry. So really, I can kind of ignore the third quadrant and kind of redraw my graphs up here in the first quadrant, drawing them in such a way that they intersect so that I know I have solutions to these equations. It's worth pointing out that if you hated this argument for how I came up with the graph in purple, you could probably talk yourself into the points 1b and b1 being on the graph in purple just by looking at this equation. Being like, if x equals 1, what would y have to be so that 1 times y equals b? And similarly, if y equals 1, what would x have to be? I don't know, whatever. Function transformations are really powerful and probably good to review, but maybe not totally necessary for this problem. So anyways, what we're trying to figure out is which of these criteria, what will the relationship between A and B have to be, to make sure that we have at least one solution. So first off, just kind of thinking about this thing, if we choose B to be whatever arbitrary number it was that creates this graph, then we're going to have intersections whenever the circle is big enough to intersect this line, right? If A were super small, I'd have this tiny little circle that looks something like this and it wouldn't intersect the graph in purple. So generally speaking, large values of A for a given value of B are good. They're going to cause intersections. They're going to give us solutions. So when you look at these different answers, you kind of know immediately that this ain't going to be the answer, and that this ain't going to be the answer, and that this ain't going to be the answer. Because in all three of these cases, we need A to be less than or equal to some given value of B. And that doesn't make sense. When A is really small, that's when we don't have intersections. We need A to be sufficiently large for the circle to intersect the graph in purple. So without even doing any real analysis, we've narrowed the answers down to two possibilities. I guess that's kind of nice. So which of these two is right? Well, I bet there's lots of different ways you can solve this, but the way that made the most sense to me is sort of thinking about the extreme case. I guess I'm looking at this picture here. Thinking about A being as small as possible so that it still intersects this line. Right? And this circle, this dotted circle here, it's supposed to be a circle. It's not a great drawing, but whatever. Instead of getting two solutions in the first quadrant, I just get one solution in the first quadrant. And if A were any smaller than this amount, I wouldn't get any solutions at all. Another way of thinking about that is I'm going to get a solution anytime A is greater than or equal to this magic amount that I drew right here. So what is this magic amount? Well, there's a lot of ways you can figure it out, but what I did is I took advantage of the fact that in the case where I have one intersection in the first quadrant, it has to lie on this line y equals x. That's just a consequence of the symmetry of these two graphs. And one way of characterizing this point is by saying that the distance from the origin to this point on the dotted graph in red is the exact same as the distance from the origin to this graph in purple. What's the distance from the origin to this graph in red? Well, remember, the graph in red is a circle centered at the origin, so the distance from that center to any point on the circle is always equal to the radius, which I'll call the square root of A. I know that's a little bit misleading because I have A labeled here. Maybe you'll allow me to just kind of cross this one out and change A into the number so that the square root of A represents this radius. What's the distance from the origin to this point on the graph in purple? Well, maybe that's a little bit less obvious. One way you can figure it out is you can think about the distance formula is just the square root of the difference in the x coordinates squared plus the difference in the y coordinates squared. You can sort of think a squared plus b squared equals c squared. If you square both sides of this equation, really all we're doing is using Pythagorean theorem on this right triangle right here. This is the difference in the x's, this is the difference in the y's, this is the distance that we're looking for. Anyways, I can use this formula. One of the 2 points that I'm trying to figure out the distance between is the origin. So x1 is 0 and y1 is 0. The other of the 2 points is whatever the hell this point is right here. Well, because it's on this graph in purple, it must satisfy this equation. And because it's on the line in green, the y coordinate must be the same as the x coordinate. So I have two equations. I can kind of solve one for y, already done, and plug it in over here. And I get x squared equals b. So x is plus or minus the square root of b. But since I'm in the first quadrant, I know it's positive. Using that same logic, except now we're changing all the x's into y's. I get y squared equals b. So y is the square root of b. What I'm saying is this point that lies on the graph in purple and also on the line in green has an x coordinate equal to the square root of b and a y coordinate equal to the square root of b. Oh yeah, that makes sense. Clearly it's on the line y equals x, and it's on this line because if I take the square root of b and multiply it by the square root of b, I get exactly b. What I'm saying is that x1 is root b and y1 is root b. Plugging those into the distance formula, I get the square root of root b minus 0 squared plus root b minus 0 squared. In other words, the square root of 2b. I'm going to get this point of tangency and one solution in the first quadrant anytime the distance from the origin to the graph in purple is the exact same as the distance from the origin to the dotted graph in red. And that'll happen anytime the square root of a, the distance from the origin to the dotted graph in red, equals the square root of 2b, the distance from the origin to the graph in purple. We can solve this equation by squaring both sides of the equation. We get that a is equal to 2b. So we get exactly one solution in the first quadrant if a is equal to 2b. And if the radius of this circle is any bigger than that, in other words, if a is greater than 2b, then we'll get two solutions in the first quadrant. The question is looking for anytime we'll get one or two solutions in the first quadrant. So that'll happen anytime a is greater than or equal to 2b. Going up to our solutions here, it looks like that's solution A. I'm sure there's lots of other ways you could solve this problem, but exploiting this idea of distance kind of made the most intuitive sense to me. But if you come up with anything really clever or just good alternatives to share, please put them in the comments.